Thank you very much. Thank you all for coming this early in the morning. So I'm going to talk about two different kinds of exchange innovations in exchange design that have gotten a lot of traction in the blockchain space. At the high level, these are batch exchanges and constant function market makers. Some of these you have seen before, but the question here is that what happens when the two of them get combined? And this is not just like an abstract theoretical exercise that I cooked up for myself. This happens a lot in practice, both in industry and academia. But when you put them together, they sort of subtly don't fit together. So there's an extra degree of freedom, and different projects take different choices, which leads to subtly different results. And so my goal here is to map out this design space so that people can start making informed decisions. Right. So the basic model here is that we have n different assets. They're all divisible and fungible. And we have a bunch of users that are trading from one to another with standard limit orders, right? Sell some amount of one for another asset at some limit price. It's pretty general. Right? No, the standard way of doing this is with a central limit order book. For a lot of reasons, this doesn't work well on today's blockchains. And so instead, one way that you can do this in today's systems is what's called a batch exchange. Right? Instead of executing trades one by one against a central limit order book, these systems execute them in batches. The way this works is that there'll be some, what we'll call like a pricing engine that looks at the list of limit orders, comes up with a price for every asset. And then, of course, these prices, the quotients imply exchange rates. And so once we have these implied like batch exchange rates, we can go through all the limit orders and just check, does the batch exchange rate, like, is it greater than my limit price? And then limit orders make their best response to the market prices. And if I've done this right, if the pricing engine is correct, then at the end of the day, everything sells. Right? There's no surplus or debt at these batch prices. The way this works internally is that you can model this system as an instance of an arrow-to-row exchange market. You compute the equilibrium of the market, and there's a lot of nice theory here. In particular, subject to certain basic regularity conditions, these equilibrium prices are unique. Right, so if I'm running a batch exchange, I just have to like run some algorithm to get the prices, and I don't have to make strategic decisions about how I'm like setting prices in this system. Right. There's a lot of work on this kind of model, but the key features that I want you to think about for this talk is that all of the economic properties of this system, which economists have been discussing for a while, come from the fact that we're settling all trades at these uniform prices. And so we'd like to like maintain that with like whatever we do. Of course, also, if we want to like instantiate this in practice, I have to be able to efficiently compute these prices, these exchange market equilibria with concrete efficiency. Great. So the other thing, it's gotten a lot of traction, are these constant function market makers. We had a talk yesterday about them. The basic point, all you need to know for this talk is that we'll have this automated system that maintains reserves of, say, 2 different assets, or n different assets, really. And we'll also have some trading function, which is this blue line. Great. And if you think of the amount of assets of like x and y that you have, that maps to a point in the xy space, and then this constant function market maker will accept a trade if and only if you stay above this blue line, right? You can think of the slope of this line as like the spot price, which is the exchange rate that you get for like an infinitesimal size trade, right? Why do people do this? Well, you need some market making in order to add liquidity to any kind of exchange, and this is an automated and computationally simple way of doing that. So it runs well on today's blockchains. Great. So we have our 2 mechanisms for doing exchanges on a blockchain that are both well-defined, fairly straightforward. There's no like intermediary here that's like making strategic decisions. But now there's suddenly in the last couple of years, there's been a bunch of projects in industry and in academia that try and put them together. And as I said, each of these projects makes slightly different decisions on how they get matched together. So what I'd like to do is start mapping out the design space for these different projects. So let's start by just characterizing like exactly what we need in the combined system. Right? Again, we have n different assets. We're going to think about this as we have one batch exchange we'll have a bunch of CFFMs that the batch exchange might plug into. And then there's this outside world. I'm going to keep that deliberately vague because how this system interacts with the outside world is going to affect the decisions that we make. Right. So of course, we need to make sure that we don't create assets out of thin air. And we'd like to maintain this uniform price notion that got us the nice properties of the batch exchange. We'd also like to make sure that the limit orders make their best responses to the market price. Your limit order is going to trade if and only if its limit price is less than the batch price, and it's going to trade at the batch price. These are standard market design assumptions. These kinds of things lead to classic theory results on error-to-row exchange market equilibria. So there shouldn't be anything controversial here. We also need to make sure that if we're going to talk to a CFFM, we need to make sure that the trading function doesn't decrease. Again, this is just the basic property of the CFFM. However, suddenly now we no longer have a unique market equilibrium. That's just because you can visualize the batch price as this orange line, right? And now suddenly, what trade should the CFFM make? Right, there's this whole space between the CFFM trading curve and the upper bound of the batch price. So now we, as the market designer, have to make a choice about what trade should we make with the CFFM. There's a bunch of natural choices, right? You can think about trading along the curve until your spot price is equal to the batch price. You could think about sort of trading as much as possible, or picking the equilibrium where the CFFM trades as much as possible. That's sort of trading from our initial reserves all the way over to, I give up on this better. All the way over. You can also think about the CFFM trading function as the portfolio value function and maximizing that, right? That gets you to point C. So what do we do? Right. Well, let's think about what we might want. Let's think about what we might want in the combined system. We might like it to be Pareto optimal from the perspective of the traders. Right. Again, before we added CFFMs, we sort of guaranteed Pareto optimality by default. We also might like what we'll call price coherence. This is just saying that after we settle a batch, the spot prices of the CFFMs should all be in a coherent state, right? Every CFFM trading between X and Y should have the same spot price after the batch. The reason we care about this, we might care about this, is that whenever that's not the case, there's a free arbitrage opportunity left on chain. So somebody can come along and sort of basically make a bunch of trades to realign the spot prices. That looks like free money, and competition to acquire that free money basically incentivizes a DOS attack on today's chains. We also might we can weaken that, say that we're not going to necessarily eliminate all of these arbitrage opportunities, but maybe we're not going to create them, right? Turns out we can't get both of these. It's basically fundamentally impossible to guarantee both, and that's just because if you want to ensure Pareto optimality for the limit orders, that can require you to make maximal usage of all the liquidity that you have on the CFFMs. And that basically requires you, or can require you, to trade all the way across. And once you trade all the way across until you hit the hard constraint, you have no control over the spot price after the batch. Another thing you might like is for the CFFMs to quote unquote learn the batch price. If you assume that the batch price is going to be arbed to be equal to, say, the price on a centralized exchange, this is essentially allowing the CFFMs to benefit from that kind of price discovery. That basically means you have to maximize the CFFM trading function, trading to point C, essentially. And again, this suffices to guarantee price coherence at the cost of Pareto optimality. And I also want to point out, this is an example of how the context in which we put the system matters. Right? If I'm trading to this point C, again, that prevents this cyclic, these arbitrage opportunities, but that actually incentivizes me as a user to try and split my trade into 1,000 tiny pieces, because that'll get me a better rate. And so the question here is really, how often are batches happening, and who gets to decide the composition, and who gets to decide the batch frequency, right? Another thing we might like, just to make the computation process efficient, is to narrow the search space for the set of equilibria. And one natural way to do that is to make each CFFM's trade locally computable, right? Maybe the CFFM's trade depends only on, we'd like to make CFFM's trade depend only on the batch price and not like everything else that's happening in the batch. Of course, as we said, like trading to this point C is the only thing that guarantees price coherence. But I want to point out, we can also guarantee this like weaker notion of price coherence by trading all the way across only in one unique case. And that one unique case is when everyone's using this Uniswap style constant function trading goal. Basically, that has a lot of symmetry to it. And this is actually the unique exception to the theorem I had before, where we had this incompatibility between period optimality and price coherence. I just want to wrap up by discussing how we actually could compute these equilibria in this combined system. There's a lot of different approaches that the literature takes, things like mixed integer programs, or just write the whole thing down as this big constraint set and throw it at some non-convex solver. Once we have this notion of local computability, then we can run algorithms based on auctions or iterative processes. We need certain regularity conditions that are standard in the literature, but once we have that, standard approaches to solving error-to-borough exchange markets can be applied. I just want to wrap up by discussing one particular convex program for this problem. I said before, in the standard batch exchange model, you can model it as this error-to-borough exchange market. These limit orders map to linear or agents with linear utility functions in that model. And I think we generally tend to talk about CFFMs as trading between like n different assets, but if we're restricting ourselves to the case of CFFMs that trade between just two, which is the standard, I think, in practice, then you can actually decompose the CFFM into this like continuum of limit cell orders. We can take advantage of that to get a nice convex program. Right, so here's the convex program for the standard linear error-to-borough exchange market case. Don't try and parse this, right? Just point out the objective is like summation over limit orders, right? And when we put this into the case with CFFMs, we swap this into this like integral over a density function over limit orders. Equivalently, this kind of program solves the case of error-to-borough exchange markets where there's many different assets, but every agent has utility only for two, subject again to like certain regularity conditions. And this is a class of utility functions that it seems less studied in the literature relative to how often it shows up in practice, right? And this is one example of how it's actually has as a special case, it's like particularly tractable to analyze. So just to wrap up, right? What have we done, right? Well, we've given an axiomatic framework for thinking about how batch exchanges can take advantage of the liquidity available on today's passive constant function market makers. Where we have these two basic mechanisms. They're both well-defined and like sensible on their own. Once we put them together, we have this extra degree of freedom that if we're going to use that, we have to make deliberate choices about how we're going to use that. And those choices have real consequences. Fundamentally, certain natural desirable properties are incompatible, right? We can't guarantee Pareto optimality and also prevent these arbitrary opportunities from being created. And along the way, we find a nice convex program for handling this particular case of error-to-borough exchange markets that seems to show up naturally in practice. Thank you very much.
Are there direct implications for some of the batch options that have been deployed? You mentioned like cash swap number at the beginning. So where do they fit into this picture?
It's a little hard to tell because I think the biggest is like CowSwap, and they're sort of constantly changing what they're doing. I think the biggest choice that I see is switching between like trading all the way across versus sort of maximizing the trading function. What happens in practice is that people tend to pick like the pre-optimal from the point of view of the limit orders option. I think again because it's pre-optimal for the limit orders. Yeah.
You mentioned a very interesting thing, which is you can have both conditions in a case where this thing is a constant product market maker. What's the intuition for that? Given I assume it comes from a convex program and some logs or something. But
no, they have a lot of symmetry, and so I start at some spot price. I have the batch price, and I have the final spot price. And there's a nice algebraic relationship between these, which is not the case for general CFFM trading functions. But because it's a product, I can like write this down and I forget the exact thing, but
But it's explicitly because it depends on the fact that the output is like whatever RA or RB and stuff.
Yeah.
And like, that's the only one that can,
that's the only, yeah.
Okay.
That's the only that guarantees it like in general, right? I mean, certainly you can construct special cases and like narrow cases, but.
Okay, so like there are no other consequential market makers, no other trading function that would satisfy this.
Not outside of like isolated cases, yeah.
All right,